The magnetic properties of a compound can be determined from its electron configuration and the size of its atoms. Because magnetism is generated by electronic spin, the number of unpaired electrons in a specific compound indicates how magnetic the compound is. In this section, the magnetism of the d block elements are evaluated. These compounds tend to have a larger number of unpaired electrons. Diamagnetism and paramagnetism are often affected by the presence of coordination complexes, which the transition metals readily form. This article mainly discusses paramagnetism. The spin of a single electron is denoted by the quantum number ms as plus half or minus half. This spin is neglected when the electron is paired with another but creates a weak magnetic field when the electron is unpaired. More unpaired electrons increase the paramagnetic effects. The electron configuration of a transition metal changes in coordination complex. This is due to the repulsive forces between electrons in the ligands and electrons in the compound. Depending on the strength of the ligand, the compound may be paramagnetic or diamagnetic. After studying this module, you shall be able to know about the paramagnetic properties of different materials, learn about definitions related magnetism, identify the different types of magnetic bodies, evaluate the factors responsible for the different magnetic behavior of the different materials. Magnetism is a property of matter in which there is force of repulsion or attraction between like or unlike poles. Only a few solid materials are naturally magnetic. Magnetism arises from moving charges such as an electric current in a coil of wire. In a material which does not have a current present, there are still magnetic interactions. Atoms are made of charged particles which are moving constantly. Because we cannot see magnetism, a model or mental picture can help us visualize the atom that make up the solid. Electrons in most atoms exist in pairs, with each electron spinning in an opposite direction. Each spinning electron causes a magnetic field to form around it. In most materials, the magnetic field of one electron is cancelled by an opposite magnetic field produced by the other electron in the pair. The atoms in materials such as iron, cobalt and nickel have unpaired electrons, so they don't cancel the electron magnetic fields. As a result, each atom of these elements act as like a very small magnet. The processes which create magnetic fields in an atoms are: first, nuclear spin, that is, some nuclei such as hydrogen atom have a net spin which creates a magnetic field. Second, electron spin. An electron has two intrinsic spin states which we call up and down, or alpha and beta. Third, electron orbital motion. There is a magnetic field due to the electron moving around the nucleus. Each of these magnetic fields interact with one another and with the external magnetic fields. However, some of these interactions are strong and others are negligible. Some important definitions. A dipole consists of a positive and a negative pole separated by a small distance. A pole is where the magnetic effect is strong, whether it is the north or the south pole. A dipole generates its own magnetic field or flux, and this field or flux can be mapped out from the directions assumed by a small compass needle suspended in the field. The north end of a compass will align itself with the field such that it points toward the south pole of the magnet. Magnetic pole strength. Unit pole strength is defined as the strength that repels as identical pole 1 centimeter away with the force of 1 dyne in free space, or we can say vacuum. The force is attractive if poles are of opposite sign and repulsive if of like sign. Or pole strength is the measure of the force exerted by one face of the magnet on a face of another magnet when both magnets are represented by equal and opposite poles. Pole strength and line of force. A magnetic field of unit intensity is taken to give a unit line of force per centimeter square. If a pole of strength m is enclosed in a sphere of radius 1 centimeter, a total of 4 pi p lines force will originate from the pole, the surface area of the sphere being 4 pi centimeter squares. This is Gauss's law. The number of lines of force per centimeter square at the surface of the sphere is given by 4 pi p divided by 4 pi is equals to p. Magnetization. When a magnetizable material is placed in a magnetic field, it will become magnetized in the direction of applied field. The intensity of this induced magnetization, which we call the induced magnetization, is expressed in terms of pole strength induced per unit area, that is m is equals to p upon a. Magnetization will disappear when the field is removed. For a magnetic dipole of length L and pole area, we can write m is equals to p into L divided by a into L, which is equal to magnetic moment divided by volume. Here m represents magnetization, small m is the vector that defines the magnetic moment, capital V represents volume, capital N is the number of the magnetic moments in the sample. The quantity N by V is usually written as small n. The number density of magnetic moments, the M is measured in amperes per meter in SI units. Thus, magnetization may be alternatively defined as magnetic moment per unit volume. Intensity of magnetization. Intensity of magnetization or magnetic polarization I is defined as I is equals to mu naught m, where mu naught is the magnetic permeability of the vacuum. I is measured in Teslas. This allows an alternative description of all magnetization phenomena in terms of the quantities I and B, as opposed to the commonly used M and H, magnetic field or magnetic induction. The magnetic field B due to the pole strength PL at a distance r from the pole is defined as the force per unit positive pole at the point. It explains B is equals to mu naught P1 divided by 4 pi mu r square. Magnetic field B is sometimes called magnetic induction. When a magnetizable material is placed in magnetic field of strength H, the total lines of force coming out per unit area of the body is given by the sum of H and the additional field delta H due to the induced magnetization, since M is the pole strength induced per unit area. So the magnetic induction B is given by B is equals to H plus delta H, that is equals to H plus 4 pi M. That becomes B divided by H is equals to 1 plus 4 pi M upon H. That gives mu is equals to B upon H, that is equals to 1 plus 4 pi chi V, and that again gives us B is equals to mu naught H plus M, that is mu is equals to B upon H is equals to mu naught 1 plus chi V, where B is the magnetic field within the substance, H is the applied magnetic field, and M is the magnetization. Mu naught is known as the magnetic constant or the permeability of free space, and chi V is the volume magnetic susceptibility, magnetic permeability, mu. Magnetic permeability is the measure of the ability of a material to support the formation of a magnetic field within itself. In other words, it is the degree of magnetization that a material obtains in response to an applied magnetic field. Magnetic permeability is typically represented by the Greek word mu. The reciprocal of magnetic permeability is magnetic reluctivity. Mu is equals to B upon H is equals to 1 plus 4 pi M upon H. That becomes mu is equals to B upon H is equals to 1 plus 4 pi kappa, where mu or B upon H is called magnetic permeability of the material. Kappa is the magnetic susceptibility per unit volume. By definition, kappa in a vacuum is 0, so that B is equals to H. Magnetic permeability is also defined as the ratio of the density of lines of force within a body and under vacuum. In SI units, permeability is measured in Henries per meter or Newtons per ampere squared. The permeability constant mu naught, known as the magnetic constant or the permeability of free space, is a measure of the amount of resistance encountered when forming a magnetic field in a vacuum. But the magnetic constant has the exact value, that is mu naught is equals to 4 pi into 10 raised to power minus 7 Henries per meter. Relative permeability, sometimes denoted by mu r, is the ratio of permeability of a specific medium to the permeability of free space mu naught. Means mu r is equals to mu upon mu naught. Volume magnetic susceptibility, the ratio M by H is the magnetic moment per unit volume, per unit magnetic field, and is known as the volume magnetic susceptibility kappa of the material. It is a characteristic property of a material, as we know that M is proportional to H. Therefore, M is equals to kappa H, that give us kappa or chi V is equals to M by H, where M is the magnetization of the material measured in amperes per meter, and H is the magnetic field strength also measured in amperes per meter. Chi V is therefore a dimensionless quantity, gram or mass susceptibility. It is usually more convenient to measure gram susceptibility chi G, which is related to volume susceptibility through the density. So, chi G is equals to kappa upon rho, where rho is the density and kappa is the volume's magnetic susceptibility. Molar susceptibility chi M. Finally, to get our measured quantity on a basis that can be related to atomic properties, we convert to molar susceptibility. Chi M is equals to chi G into capital M, where capital M is the molecular weight of the sample. Magnetic moment. In magnetochemistry, the magnetic susceptibility is not used for the discussions. In fact, magnetic moment is more convenient property to use. If a bar magnet is placed in a uniform magnetic field H, its pole plus P and minus P experience force plus pH and minus pH along and opposite to the direction of magnetic field H. So, net force on the bar magnet is 0. Torque on the bar magnet, it explained F is equals to pH minus pH is equals to 0. But force being equal and opposite and having separation between their lines of action form a couple. The moment of force or couple is given by tau is equals to force into perpendicular distance. So, tau is equals to pH into Bn, that becomes pH into 2L sine theta. The product P dot 2L gives the magnetic moment M of the substance or magnet. So, the equation becomes tau is equals to mh sine theta. If theta is equals to 90 degree, then the torque is maximum and given by tau maximum is equals to mh. Thus, mh is the measure of the work done by the magnetic field in rotating the magnetic dipole by 90 degree. It explains from a position perpendicular to H to one parallel to H. The magnetic susceptibility of any substance is determined experimentally. The magnetic susceptibility is then converted to the magnetic moment using Curie equation. It should be noted that magnetic susceptibility is an additive property, whereas it is the square of magnetic moment that is additive. Types of magnetization. The relation mu is equals to B upon H is equals to 1 plus 4p kappa easily predicts two class of magnetic bodies. When mu is equals to 1, it explains kappa is equals to 0 and B is equals to H. Thus, mu r is equals to 1. These materials do not lead to a channeling of the magnetic field and are said to be non-magnetic. For example, sodium, aluminium and magnesium. Diamagnetism. When susceptibility kappa is negative, we have mu lower than 1 and B again lower than H. The substance is called diamagnetic. It explains the magnetization opposed magnetizing force. It arises from the precision of spinning charges in a magnetic field. Such a substance allows a smaller number of lines of force to pass through it as compared to that in vacuum, and therefore prefers to move the region of the lowest magnetic field strength. The magnetization is in the opposite direction to that of the applied field. It explains the magnetic susceptibility is negative. That means chi m is lower than 0. Diamagnetism is a very weak form of magnetization that is only exhibited in the presence of the external magnetic field. It is the result of changes in the orbital motion of electrons due to the external magnetic field. The induced magnetic moment is very small and in a direction opposite to that of applied field. There is thus a weak negative susceptibility and a relative magnetic permeability of slightly less than 1. When placed between the poles of a strong electromagnet, diamagnetic materials are attracted towards region where the magnetic field is weak. Diamagnetism is found in all materials. However, because of it is so weak, it can only be observed in materials that do not exhibit other forms of material. Also, diamagnetism is found in elements with paired electrons, for example, silver, gold, copper, lead, zinc, etc. Paramagnetism. On the other hand, when kappa is positive, we have mu greater than 1, that means B greater than H. The substance is called paramagnetic. Such a substance allows a more lines of force to pass through as compared to the vacuum. Therefore, prefers to move to the region of the highest magnetic field strength. In paramagnetism, the atoms or molecules of the substance have net orbital or spin magnetic moments that are capable of being aligned in the direction of the applied field. The alignment of the atomic dipoles with the magnetic field tend to strengthen it and is described by relative magnetic permeability. It explains mu r is equals to mu upon mu naught is equals to 1 plus chi m is greater than 1, mu m is greater than 0. Paramagnetism occurs in all atoms and molecules with unpaired electrons. Example given: free atoms, free radicals and compounds of transition metal containing ions with unfilled electron shells. It also occurs in metals as a result of the magnetic moment associated with the spin of conducting electrons. For example, aluminium, chromium, molybdenum, sodium, titanium and zirconium, etc. In most paramagnetic substances, the magnetic properties originate entirely from the individual magnetic centers. It explains there is no secondary magnetic interaction between the neighboring magnetic centers. Such a substance is called magnetically dilute. There are some magnetic substances in which there is secondary interaction between the neighboring magnetic centers. Such a substance is called magnetic concentrate substance, and the interaction it may lead to an increase or decrease in magnetic moment. A substance of type 1 is called ferromagnetic and type 2 is called antiferromagnetic. Ferromagnetism, a phenomena in some magnetically ordered material in which there is a bulk magnetic moment and magnetization is large. The electron spins of the atoms in the microscopic region domains are aligned. In the presence of external magnetic field, the domains oriented favorably with respect to the field grow at the expense of the others, and the magnetization of the domains tend to align with the field. The total magnetic moment of the substance is the vector sum of the magnetic moments of the component domains. Ferromagnetism is a phenomena by which a material can exhibit a spontaneous magnetization and is one of the strongest form of magnetization. It is responsible for most of the magnetic behavior encountered in everyday life and is the basis of all permanent magnets as well as the metals that are noticeably attracted to them. Antiferromagnetism phenomena is some magnetically ordered material in which there is an anti-parallel alignment of spins in two interpenetrating structures so that there is no overall bulk spontaneous magnetization. In ferromagnetic materials, it is energetically favorable for the spins atomic to align, leading to spontaneous magnetization. However, in antiferromagnetic materials, the conditions are such that it is energetically favorable for the spins to oppose, leading to no overall magnetization. In material that exhibit antiferromagnetism, the spins of magnetic electrons align in the regular pattern with neighboring spins pointing in opposite directions. This is the opposite of ferromagnetism. Antiferromagnetic materials have negative coupling between adjacent movements and low frustration. Antiferromagnetic materials are relatively uncommon. An example is the fermions superconductor. In this module, we discussed some important definitions of magnetic properties: magnetic pole strength, line of force, magnetization, magnetic field or magnetic induction, magnetic permeability, magnetic susceptibility, magnetic moment. In general, two types of magnetism are possible in materials: diamagnetism and paramagnetism. The magnetic substance can be magnetically dilute or magnetically concentrated substances. In magnetically dilute substances, the magnetic properties originate entirely from the individual magnetic centers. There is no secondary magnetic interaction between the neighboring magnetic centers. However, in magnetically concentrated substances, there is secondary magnetic interaction between the neighboring magnetic centers. These secondary magnetic interactions may lead to an increase or decrease in magnetic moment. A substance of first type is called ferromagnetic and the type second is called antiferromagnetic.